All right, welcome back. So not only does plate tectonics play a role in shaping the geology of a coast, whether it's an active margin near a boundary or passive margin away from a boundary, but so does the motion of the ocean near the coast also shapes the geology, what we see, the landforms that we have and see on the coast. So let's talk about moving water, specifically in the ocean. So again, water in motion helps to shape the geology of coasts, and that type of motion can include currents, tides, waves, as well as sea level rise. All of these are water in motion. We'll spend some time talking about the first three, and we'll save more of that fourth one, sea level rise, for the assignment that you'll do for this unit. But let's first start talking about currents. All right. Currents are a movement of ocean water in somewhat continuous, recognizable flows. These are mapped, have been known for for hundreds of years, and it helps us to kind of track how the water flows in the ocean. It's something like this where if you threw something in the ocean near a current, you could figure out where that stuff would eventually float to. Currents either are caused by wind, and typically surface currents. The currents near the surface are caused by wind. The wind blows across the ocean. It kind of pushes and pulls the water with it. Wind patterns are usually in the same direction, but on any point on Earth, but they blow in different directions depending on where you're at. So anyway, wind is really what causes the surface currents. Then you also have subsurface currents. A lot of that is driven by density differences in water caused by temperature and salinity variations. Colder water, more dense. Saltier water, more dense, that wants to sink. Warmer water, less dense. Less salty water, less dense, that tends to want to rise or not sink. But gravity, earthquakes, storms, all have a part to play in causing currents. But currents are really controlled by the location and shape of the continents, plate tectonics. Currents, as they flow in the different oceans, are bounded by land, so where the continents are. In the geologic past, millions of years ago, with the plates in different locations, currents were different. Currently, though, this is a good generalized map of the ocean currents. The pink are more so warm ocean currents. The blue are cold ocean currents. So we have the highest amount of solar energy is hitting the equator, the warmest part of the globe, on average. And so then you take that warm ocean water in the northern hemisphere, north of the equator. As that kind of warm water heads north, it cools down and warms back up again, heads back north, cools down. And it does so, in general, in a clockwise pattern north of the equator. South of the equator, that flow, known as a gyre, is counterclockwise. But you get warm water coming down, cooling down, heading back up to the equator, and that process happens over and over again. So clockwise north of the equator, counterclockwise south of the equator, which is pretty interesting as it pertains to the United States, because we have off the east coast this warm ocean current moving up, and off the west coast this cold ocean current moving down. If any of you have ever gone to California, San Diego, whatever, and jumped in the ocean, it's pretty cold. If you have ever gone over to the east coast or the Gulf states, Texas, Louisiana, Mississippi, whatever, you jump in the water there, it's nice. The water's warm. And that's due to these currents. So we have a warm ocean surface current off the east coast, but a cold ocean current, surface current off of the west coast. There you go. Just something to keep in the back of your brain. Currents also have a part to play in regards to the world's deserts. So we'll kind of revisit this next unit. Unit 14 deals with deserts, as well as kind of location of deserts in relation to kind of these two lines of latitude. So just a little foreshadowing for Unit 14. So keep this stuff in the back of your brain. But anyway, back to currents. So surface currents extend from the surface to about 200 meters below the ocean surface. That's 2 soccer fields. The deep ocean currents begin about 300 meters below the surface, and some of them can go as deep as the ocean floor. The currents really help to, besides just moving water, they really help to regulate Earth's climate by transferring heat from warm areas to colder areas. So you remember these warm ocean currents near the equator, and that in the northern hemisphere kind of clockwise circling up, cooling down, coming back down. So those currents are helping to take heat away from the equator. If not, the equator would just get hotter and hotter and hotter and hotter and hotter, and just you would burn to death eventually. So what this ocean water does, it actually helps to transfer that heat away from the equator a little bit, so it's not, you know, deadly. If we look at all of those currents, which there's a number of them, and we kind of mathematically average them out, they're all connected via the surface and subsurface in something called the Great Ocean Conveyor Belt. And it's all connected and all driven by something called thermohaline circulation. Thermo, heat. Haline refers to salt. So whether the ocean currents are hot or cold, whether it has more salt or less salt, all of that helps to connect all of the ocean currents, and it gives us a generalized flow called the Great Ocean Conveyor Belt. So what you're seeing here, if we kind of mathematically averaged all the currents, surface and subsurface, this is the generalized flow of water in the ocean. This is the generalized flow of water in the ocean. Like, for instance, if I'm driving from EMCC to my home, I have to head north, then I head east, then I head south. All right, so that's kind of all over the place. But in general, I could, if I were able to fly, I could just fly east to my house. So what this map is that generalization. If I average all of that direction of movement, I'm just going from here to there. Well, all of those currents that we looked at on the previous map, you average them all out. This is kind of the flow that you would get in general of the ocean. You get a warm surface flow, kind of cooling down. So again, thermohaline circulation, cooling down, sinking subsurface, peeling off in a couple directions to the Indian Ocean, or continuing to the Pacific Ocean, where it raises back up to the surface, warms up again, cools down, sinks. Again, this is the generalized current flow of all the water in the ocean. What's important to note is this spot right here. This spot right here, where this warm ocean water kind of cools down, becomes dense, and sinks. That's very important, this spot right here. If any of this gets messed up, well then, you know, the currents get messed up, then the climate gets messed up. So, just kind of bad news. So, let's go ahead and take a pause here. When we'll come back, we'll talk about some of that bad news, and specifically we'll talk about the Gulf Stream here in just a minute. So I'll see you then.